Hello, class. So on the previous video, we were talking about how to use the properties of integrals, right, of definite integrals. We saw that a couple of them were the same as the properties of indefinite integrals. For example, if you have a constant times a function, you can move it out of the integral. If you have a sum of functions inside the integral, you can separate it as the integral of each function separately and then add them. Other things were kind of like more, it's just kind of intuitive. So property 2, you can, if you have you're trying to calculate the net area of a region of length 0, well, it doesn't matter the height, that area is going to be 0. 5, property 5 was used, you can separate the integral as into intervals, right, smaller intervals, as long as those intervals add up to the whole thing. And then we also talked about how to find the area of a function instead of net area using definite integral notation. Just take the absolute value of a function. And the last property was this sort of like not intuitive one, that if you want to change the order in which you take your bounds, so instead of going from 1 to 2, you want to go to from 2 to 1, you can do that, just put a minus in front. Again, for us, it's not going to be as useful other than in, theoretical examples like I gave you here in the previous video, or once we start working with antiderivatives again. So that was the last video. For this video, we're going to end up on something that's hard, and after you see how this whole works, you're going to be thankful that we won't be having to do this all the time. We want to use the definition of a definite integral to evaluate integral from 0 to 2 of x minus 1 dx. Now remember that by definition, this definite integral, well, it's two things. It's net area, but it's also this limit here, which consists of two things, right? It consists of an approximation using n subintervals. Right? That's what this is. So reminder, this is an approximation using n subintervals of the area, so approximation of net area using n subintervals. That's the first part of this thing, and there's also this limit. Right? So what we're going to do is we're going to tackle this in parts. We're first going to see what this approximation is, and then we're going to calculate the limit of that approximation. You're going to see it's a lot of work, and you're going to be thankful that there's an easier way to do this. So first, let me start here. Let's start with, and this looks kind of weird. Let me rewrite it. Let me start with the sum k equals 1 to n of f of x sub k times changing x. Again, all this is just an approximation of the net area. We know how to do this. The thing is, basically what we're gonna do is we're gonna do this again, but it's gonna be a little bit different. So one thing that we learned is that based on the theorem, as long as f is continuous, which again, f being continuous is the same as f being integrable, as long as f is continuous, this whole thing here exists. That's one thing, okay? Not only that, that also told us that this limit is going to be the same independent of what endpoints we choose in the approximation. So remember, this x sub k's are the inputs in each subinterval where we evaluate the function in to get the height of each rectangle. Okay? So by a theorem, the theorem that we saw in the previous section, doesn't matter what approximation we use, it's always going to give us the same answer. So what we're going to do is we're going to do a left endpoint approximation, a left Riemann sum. So some things are the same. We first want to find change in x, right? So this is going back to the examples we did in section 5.1. Right? How to do a left Riemann approximation. I don't know if it was 5.1 or 4.9. I think it was 5.1, because 4.9 was antiderivatives. Okay, so let's change in x. Well, you always subtract the endpoints of your interval and divide by the number of subintervals. Remember that the endpoints of the subinterval are given by these values. So the interval is the interval 0 to 2. So what's the formula? We'll subtract the endpoints. So 2 minus 0 is 2. How many subintervals are we doing? Well, again, by definition, this is an approximation that's using n subintervals. So we're going to divide by n. Right? So our change in x is 2 minus 0 divided by n, which is 2 over n. Now, Change in x is always the same. Again, as I mentioned, it doesn't matter what approximation we use. Since this thing exists, it's going to be the same. So we're just going to use the left endpoint approximation. You could try a midpoint. You could try a right endpoint. You would get the same thing in the end. Okay? So let's go to the next page. Now, let's divide our number line into, so actually, let me erase some things here so that we can go over it again. So basically what happened is that I was doing a more complicated function than x minus 1, and it ended up being a lot of work. And the video was too long. So I don't want to do that anymore. So I basically simplified the function. Instead of squaring x, I'm just taking x minus 1. So let's first divide our interval. We want to divide our interval 0 to 2 into n subintervals at length 2 over n. Well, we know how to do that, right? We just start on the left endpoint and add changing x each time, right? So start at 0. Add changing x, we get to 2 over n, right? Because changing x is 2 over n. Now add 2 over n again. So we get to the next endpoint. That's 4 over n. Add 2 over n again. That's 6 over n, etc. until we get to the end. Now let me do something here. Let me erase this part. Now, how do we know what is the last interval subdivision before 2, before the endpoint? So let's say I want to know what this is here. What's z? Let's call that z. Well, just as you can start at the left endpoint and add changing x each time, well, you can also start on the right endpoint and subtract changing x each time until you get to the left endpoint. Meaning that what is this z here? Well, z here should be just 2 minus changing x. So you subtract changing x. So 2 minus 2 over n. If you get a common denominator, that is 2n over n minus 2 over n. Simplifying, that's 2n minus 1 over n. So we know that this subinterval division before we get to 2 is 2 times n minus 1 over n. So I wanted to do that so I can show you that you can go either left to right or right to left. I don't think that's something that I mentioned before. So just throwing that out there. Okay, now, what are we trying to do? We're trying to rewrite the sum k equals 1 to n of f of x of k, changing x, so that it fits this particular example. Well, changing x, we already know what it is. So this is the sum k equals 1 to n of f of x of k. Changing x was 2 over n. What is the hard thing here? What's going to be hard is finding what x of k is. Because x sub k should be the endpoint in the kth subinterval. Remember that these indices here, when k equals 1 to n, we're saying that we're summing over each subinterval. So what is the idea? What is the idea? Well, when k equals 0, well, when k equals 1 at the first subinterval, what should be our endpoint? Well, we're using the left endpoint approximation. You can just look at our picture here. The first left endpoint is 0. So at k equals 1, our x of k should be equal to 0. When k equals 2, and we're on the second subinterval, our left endpoint is 2 over n. So x of k, which is again is the input, should be 2 over n. When k equals 3, our input should be the left endpoint of the third subinterval. Well, that would be 4 over n, etc. all the way. So we get to k equals n. That's the last subinterval. And we know that the input should be, well, we're doing left endpoint. So the last left endpoint is this thing that we found, 2 times n minus 1 over n. Okay. Now, what's going to be the hard thing? If you go back to section 5.1, whenever we want to write a sum as a sigma sum, so in this notation here, we always have to identify the thing that changes and write it in terms of k. What is it that is changing here? The changing x stays the same. The function stays the same. What's changing is the input, as we saw. So what we're going to try to do is write the input in terms of k. Well, a good contender is, we already see the pattern here. We know that the pattern is something like this. So what if we try here? We're going to say that we're going to use x of k to be so we're going to set x of k to be 2 times k minus 1 over n. So meaning that when we plug in k equals 1 into 2 times k minus 1 over n, that should give us 0. When we plug in k equals 2 into 2 times k minus 1 over n, that should give us the next endpoint, which should be 2 over n. So let's check if this works. So if we plug in k equals 1 into this expression, we get 1 minus 1 is 0, times 2 is 0, divided by n is 0. Anything 0 divided by anything is 0. So it works for the first one. Now plug in k equals 2. 2 minus 1 is 1, times 2 is 2, divided by n is 2 over n. So it works for the second subinterval. Plug in k equals 3. 3 minus 1 is 2, times 2 is 4, divided by n is 4 over n. So we see that this formula actually works. Finally, plug in k equals n, and we get what we should be getting, 2 times n minus 1 over n. What does this mean? Well, we can write the input in terms of k, but just writing x of k equals 2 times k minus 1 over n. Now, I know this is hard, and I know I'm going a little bit fast. I'm doing this so that the video length stays short. Then you can always go back, pause the video, and think about things as we go. So what does this mean for us? This sum, k equals 1 to n of f of x of k, so changing x was already 2 over n, becomes the sum, k equals 1 to n of f of what? Well, we already wrote x of k in terms of the indices. This was 2 times k minus 1 over n times 2 over n. Now we can just simplify this here. Why? Because we're given what our function is. We know that our function is x minus 1. So you just plug this in. Right? So what's f of 2 times k minus 1 over n? We'll just plug that in for x. So this is just 2 times k minus 1 over n minus 1. Now I'm going to get a common denominator for reasons that you'll see later. I'm going to write 1 as n over n. So this becomes this. So finally, we plug all of this in. So now we know that this whole thing here is equal to this thing here. And what do we end up with? We end up with the sum, k equals 1 to n, of 2 times k minus 1 minus n all over n times 2 over n. And this is the left approximation that's specific for our example. Now here, I'm going to review some properties of sums that are nullify mentioned. If you have a constant times an expression, so the expression of k, you can move the constant out. So similar to what happens with integrals and derivatives. Similarly, if you have a sum of a function involving k plus another function involving k, you can separate it as the sum of the first one plus the sum of the second one. Now this is going to be useful when we simplify this because, for example, this 2 over n is a constant. If n were 5, it would just be 2 over 5, which means that we can move this out. This 1 over n here is also a constant, so we can move it out. So what do we get here? We get, so I'm moving out 2 over n, and I'm moving out 1 over n. Right? Those are factors multiplying n that are constants. So I'm going to get 2 over n squared when I factor both of those out. And I get the sum k equals 1 to n of whatever's left over. 2 times k minus 1 minus n. Now I'm going to use the second property to rewrite this as the sum 2 divided by n squared of the sum k equals 1 to n of the first part, 2 times k minus 1, plus 2 over n squared times the sum k equals 1 to n of the second part, which was minus n. Again, you can move constants out. Here I have a constant of 2. Here I have a constant of negative 1. So this becomes 2 times 2 is 4. So 4 over n squared times the sum k equals 1 to n of k minus 1 plus here, or minus, because I'm moving the minus outside, minus 2 over n squared times the sum k equals 1 to n of n. Let's try to simplify a couple of things. Actually, before we do that, let's here we have 2 terms in the sum, so let's divide it again. So this is 4 over n squared times the sum k equals 1 to n of k minus 4 over n squared times the sum k equals 1 to n of 1. Right? So I separated it and factor out the minus 1 out of the sum minus this thing that we have here. Now here we can simplify each of these easily if you know the right way to do it. Now let's first simplify this part. What is this saying? This says add n as k goes from 1 to n. This is saying add n to itself n times, right? So you have n terms in the sum. Each of those is n. So you add n plus n. You add n times, that's the same as multiplying by n. So this part here is just n times n. So you're adding n by itself n times. So that's just n squared. Now something similar goes on here. What's going on here? Well, we're adding 1 by itself n times. Well, that's just 1 plus 1 plus 1 n times. That's n. Finally, what is this part here? And this I don't expect you to know. But what is this saying? This is saying add the first n integers. So add k equals 1 plus k equals 2 plus k equals 3 all the way up to k equals n. There is actually a formula for that. And again, I don't expect you to know it. I'm giving it to you now. That's n times n minus 1 divided by 2. So if we plug all of this in and simplify, what are we going to get? We're going to get, so I'm just going to substitute in the things in orange, right? So here on the bottom, I have a 2. It's going to factor out with this 4. So I'm going to end up with 2 over n squared times n times n minus 1. Here, I have minus 4 over n squared times n, right? All this thing here is n. So 1 n cancels out, and I'm just left with 4 over n minus, again, 2 times, well, what do we have here? This whole thing here is n squared. So the n squared here on the top cancels with the n squared on the bottom, and this is just 2. Okay. So now we had this very complicated looking sum, because remember, this is this thing that we started with. So this was the first part. We simplified this as much as we could. Now, what are we going to do? We're going to take the limit of this. Because remember, there's 2 parts. The first part is simplifying this approximation. The second part is taking the limit of that as n approaches infinity. So for the second part, we're going to be taking the limit as n approaches infinity of the sum k equals 1 to n of f of x of k changing x, which is the same as the limit as n approaches infinity. This whole sum we saw is just equal to 2 times n minus 1 over n squared minus 4 over n minus 2. And you can calculate that limit. For example, what's the limit of the first term? Well, it's a rational function. The degree of the top is the same as the degree of the bottom. So just take the ratio of the leading coefficients. So this equals 2 here. Now what happens with 4 over n? Numerator is fixed, denominator is going to infinity, so this fraction is going to 0. So that goes to 0, that goes away. Now the minus 2 is a constant. So that the limit of that is just itself, right? So what do we get? The net area ends up being just 0. Now, of course, this is a lot of work, a lot of work. This is just one of the slides. And then we had this other slide, and then we had this other slide. So as you can see, this is a lot of work. It's doable. However, as I mentioned, in the next couple of sections, we're going to find a way to do this basically easily, right? Using antiderivatives. Now, let me just check that this is actually the right answer. Yep, that's the right answer. Okay. So what I recommend, since this is very hard, look at the example at the end of section 5.2 in the book. They basically go through an example like this. Okay. In book, obviously.